Well, good afternoon, everybody.
Thank you.
Welcome to our final brown bag for this semester. It is my great pleasure to introduce Janice Gobert, who's Professor of Learning Sciences and Ed Psych here. We were just saying this is her 5th year here already, and she's made a tremendous impact in the school, and she's always had a tremendous impact in the field. And so today, a great opportunity to learn about the system that she's been working on, and in a scholarly as well as more entrepreneurial kind of status. So, Janice, thank you.
Thank you. Thanks, Drew. Thanks so much for coming out. When I saw the snow, at least in northern New Jersey, I thought, oh no, people aren't going to come. Thank you so much. So my talk's entitled Technology-Based Materials to Support Teachers and Students on Science Practices. So today what I'm going to talk about is the context of the problem, which we all know, but just to bring that to the fore, an intro to Ngss, Inquiry Intelligent Tutoring System, and Water, our teacher platform, an overview to some efficacy data. So I want to give you a really broad kind of start, and then I'm going to do 2 fire hose studies, testing for transfer and then identifying the messy middle. And then I'm going to open it up to questions, but there's a lot of studies that have been done on this system because it's been around since 2008. So the US and many others face a STEM crisis. It's often very surprising to Americans that we're actually 25th. Canada, where I'm from, is 7th, but draw your own conclusions. We're 7. But there's lots of different reasons for that. In response to our 25th kind of ranking, by the way, which is down from 2009 where we were 13th. So that's a significant slide in 10 years. In response to that, policymakers have come up with the next generation science standards, which I'm sure all of you are very well familiar with. And teachers are required to assess these skills or practices, I use those terms interchangeably, and students need to be competent on these, but they have a lot of difficulties with inquiry. I'll talk about that more later. But these are the various practices for those of you who are not familiar: asking questions, developing and using models, planning and carrying out investigations, analyzing, interpreting data, using mathematics and computational thinking. Rachel's working on that in our system. Constructing explanations, engaging in argument from evidence, and communicating findings. And these are not mutually exclusive categories, by the way. So teachers have to, if the school or the district, the state adopts NGSS, teachers have to assess students on the practices. But there's lots of problems with typical assessments. Take multiple choice or fill in. These tend to be kind of fact, knowledge-based rather than reasoning. They're easy to grade, but they're not authentic. You have high-stakes summative, which rely on multiple choice or open response items. The feedback is given too late to help students learn, and kids struggle in silence. You have hands-on labs where students are unable to typically complete them independently. They require equipment, materials, setup time, and space. So we've interviewed 400 teachers about the problems here, and they're very difficult to grade and very difficult to grade consistently. Lab reports, which tend to go hand in hand with hands-on, use typically open response. This is a work product rather than process assessment. They're very hard and very time-intensive to grade, and they don't actually fully capture inquiry competencies. And that's the point that one of the big points that I want to make. So imagine a classroom. This is a stock photo actually, but you have all these students who are doing a hands-on lab, possibly even working on different experiments within the same class, and the teacher is running around trying to assess them on these competencies, because if their school has adopted NGSS, they actually need to provide evidence that students have mastered these practices or getting better over time. So here's an example of a boy. I like to call him Billy. Billy's a science genius. Look at how intently he's working here on his computer. He's a science genius, but he's actually not very good at describing what he knows in words. I used to work at a polytechnic university. You can't believe the amount of kids who were like this. Then imagine this boy. I like to call him John. These are just boys because this image suits it really well. And he's not even doing the experiment. He's actually just kind of trying to catch the buzz in the classroom, all right? So, but John is kind of good at catching the buzz. So when it comes to him writing a lab report or writing his claim evidence reasoning statement, he could actually write something that would pass or get a decent grade when he actually hasn't even done the experiment. Billy here is working so hard, but he's maybe not very good at writing. So Billy will be a false negative and Johnny will be a false positive. This is really frustrating to this student because he may love science and be very good at it, but his knowledge doesn't get reflected in his grade. And as a country that needs to develop more STEM competency, we're kind of tossing these kids out. This boy, for example, is one who's parroting. He'll be a false positive. This is really a problem for the teacher because she's deeming him as competent on these practices when in fact he's not. So I'm gonna tell you a little bit more about that later, but I'm just painting a broad picture here. So virtual labs can provide real-time assessment, scaffolding, and alerting potential, which is what our system does. And I want to drill down on why I think you should use simulations for this purpose. First of all, you have the affordance of authenticity, and so you have greater validity than multiple choice tests. But they're currently not used to assess the skills they were designed to foster. That's really problematic. So, you know, kids are working in these rich environments and then we give them a multiple choice test. Makes no sense. These generate rich, high fidelity log files. So while the student's working, the system can be instrumented to collect the mouse clicks, and then you can distill and aggregate those and use them for performance assessment. And that's really where I have spent the last, 15 years really developing log file analysis. So you can also give immediate feedback, blending learning and assessment, so extra time is not needed for teachers to assess students. So it's like what Val Shute calls a stealth assessment. So the opportunity for real-time performance assessment, scaffolding, and alerting is here. It's now, all right? And we have these methodological advances in computer computational techniques like data mining that offer analytic leverage on students' learning processes, not just their products, right? This is done in real time, done at scale. Scale is really important to NGSS. And none of these were possible before. Also, log files, analyzing log files can handle the 4 V's. So the 4 V's of log files are volume, the incredible volume of data, the veracity, the verisimilitude of the data to what the kid is doing, the velocity, the speed at which we're getting and collecting these, and the variability, because you're getting so much variability because it's so fine-grained. So log file analysis can handle those 4 V's. It's also, machine learning offers a very excellent approach for ill-defined problems. So when you have a very well-defined problem, like what is 2 plus 3, you don't need machine learning to actually score that because 2 plus 3 equals 5. It's always going to equal 5. There's only a couple ways to come up with wrong answers. There's only one way to come up with the right answer. So you don't need machine learning to be scoring how the student's doing that. But when you're talking about something like inquiry, where kids can do inquiry in a variety of productive ways and a variety of unproductive ways, you need machine learning to understand those patterns and have some predictive validity of what's going on. And the last thing is that when you marry together these computational techniques with these log files, it's transformative for self-assessment and real-time scaffolding, alerting, etc. So the time is now for this, right? We have an increase in online and hybrid schools worldwide. We have not enough STEM workers. The US is ranked 25th in science. NGSS has been adopted by over 40 states. And data mining methods can be applied to logs, and they're scalable. So there's challenges. I don't want to be naive about the challenges of assessment here. So you have complex tasks, which take a longer, and you have fewer of one type. So Rich Shabelson would call this a reduced reliability issue, right? You have more than one way to conduct inquiry, so you have variability in student responses. The subtasks are not independent from each other, so classical test theory does not hold. So that, this is really turning psychometric theory on its head. Traditional measurements methods are tough to apply due to the changing skill level as students are working. But that happens really with any test, as it's evoking prior knowledge. And a theory is needed to both distill and aggregate the log data, because otherwise it's like garbage in, garbage out, right? So it makes no sense to say something like really coarse measure like, oh, Billy did 10,000 clicks, mouse clicks, and Sally only did 2,000. Therefore, just do more mouse clicks, right? That's a very illustrative and simple example. So you need a theory that will allow you to distill the data from the fine-grained clickstream data to turn it into performance assessment metrics aligned to NGSS. And so that the results are pedagogically meaningful, so that it's practical for teachers and it's useful for students. So our solution to this problem is INKITS, Inquiry Intelligent Tutoring System. These are virtual labs for formative assessment. So the teacher does what he or she would normally do, and then halfway or whatever in the unit drops in with a 1 or 2 day INKIT lab, which will have 4 driving questions, to get benchmark assessments or formative assessments on the practices, how well students are doing on the practices in the context of these DCIs, disciplinary core ideas. We have these for middle and early high school. We're developing more and more high school, physical life and earth science, and they measure content, practices, and cross-cutting concepts. There's no installation required. They work with any web browser, iPad, Chromebooks, etc. So this offers an automatic, scalable, rigorous, and economical approach. You have alerts for instruction, then you have formative and summative assessment for teachers, and then you have personalized scaffolded instruction for students. So I'm just going to drill down. This is how it works in the classroom when we say to teachers, if we're not running on a study, you know, here you go, this is what you have, right? You have the student working on the activity. We're tracking everything they do, every mouse click, every change to the widget, everything they write, every time on task. I mean, absolutely everything. Then real-time algorithms are working on that log data, generating real-time reports and alerts for the teacher. And the teacher can also run with Rex, and Rex can jump in real time. The benefit to that is if the teacher has already helped Johnny multiple times, Johnny doesn't want to be the kid that the teacher's constantly going after. She can just let Rex get him, right? So she can also, she has much more information, or he has much more information about those highly personal details about the student and can make decisions on the fly. So for students, you have authentic inquiry. You have Rex, a personal tutor, and then we have a new thing, which is student reports, because students, especially gifted students, love to know how they're doing all the time. So just to give you an overview to some efficacy data, students are more systematic with hands-on experimentation after using INKITS. So we're demonstrating this empirically using a quasi-experimental design, but it was teachers who called us and said, wow, they used INKITS last year, and now at the beginning of the year, compared to kids who had never had INKITS, they're way more systematic on their hands-on inquiry. That was a very interesting and surprising finding for us. This supports ELLs and special ed learners, kids on IEPs. We're doing a lot of work with Highland Park, just down the street, with Kathy Branchak with her special ed classroom, and it's, you know, she reports it as a total game changer, which is really exciting because typically with the strategy training studies, what you have is that really skilled kids take off even faster and do better than they would, and the kids who are not as skilled kind of peter along, but you see really nice data. Different schools are calling us and saying, it improved our test scores. We did nothing different from last year other than add INKITS, like in Arizona, Oregon, New Hampshire, Massachusetts, and our scores have gone up 20%, 21%. That's great. And what teachers are doing is they're using INKITS to get a sense of where they need to drill down on the test prep for the state performance, state assessment. Now, those kinds of assessments are not going anywhere anytime soon, although they're eventually going to go, hopefully within the time span of my career. But I don't know, I don't hold out a lot of hope on that. But, you know, it's important that teachers use the INKITS labs in support of their pedagogical practices, one of which is state performance, state assessments. And Rex helps kids learn key NGSS practices and apply them across different contexts. And I'm going to drill down on that as one of the studies. So now for teachers, since you're getting a deep sense of kind of what the product looks like, We have real-time reports. Here it's pictured with a few of the practices. The dark blue are kids who've mastered. The light blue are kids who are mastering as they're working, so the teacher doesn't interrupt them. And then yellow are the kids who are at risk. But the teacher was constantly having to go back to their desk, right? So we wanted to design an alerting platform that works on teachers' phones or their iPads, that they can literally walk around the lab. So this little invention, which is really very cool, I've spent my entire career building student software, and no students have ever called and told me how great it was, including my own 3 kids. But teachers call us all the time and say, wow, I used Ink Blotter today, and I loved it, and it was the best instructional experience of my career. I mean, we get letters, we get cards, it's really great. So let me drill down on this a little bit. So the teacher can run this in various modes. She can get the alerts in recency, right? So these are as they happen, John Marcone, Victoria, etc. These are pretend names, by the way. He or she could also switch to the class view or switch to a specific skill view using the different settings, right? So right now you see a few kids are having trouble with collecting data. She might go, well, how many kids are having trouble collecting data? Because I want to stop them now. I don't want them to get to that interpretation phase where all their data are confounded, and that will be a lost learning and assessment opportunity. I want to stop them now. Switch to the class view. Wow, 70% of my kids are having trouble collecting unconfounded data. Stop the class, screens go down. So that's very, very exciting. So you have it broken down at the sub-skill level as we have all these practices. You have John Marcone's having trouble with hypothesizing. He's struggling to understand what an independent variable is. Then you have a little bit of information on this lab and how he's done today, and then some contextual information. We're now developing another layer down to help support teachers, and Amy and Rachel are working on that, so that if teachers really don't know what to do, to help them with a really detailed advice, they can drill down. So this is a really nifty tool where a teacher can have a bird's eye view of what's going on, make a class-wide decision to change instruction on the fly, to pool a couple kids together and help them if they're all struggling on the same practice, or to do different one-on-one instruction. And we're also collecting the voice logs of one-on-one and using that to predict how students are going to do on the next opportunity they have to work on that practice. And I'll tell you a little bit more about that. So the benefits for teachers are, regarding assessments, auto-scoring greatly reduces teachers' grading time of labs and matches human scoring with up to 95% accuracy. And we're now scoring 6 or 7 practices in the NGSS. Regarding alerts, this enables teachers to give more personalized help to more students more accurately and more quickly than typical approaches. And students' performance improved from teachers' help on the next opportunity they had to do the practice on which they were helped. So Rachel's been doing some epistemic network analysis, which has shown that mostly if teachers provide practice level help as opposed to content level help, that effect is robust. Sometimes teachers tend to default to content help, but that's of course not going to help them on the next opportunity because they may be switching to a different topic. So here's a broad overview of development. So we have these simulations, we have 45 of them for our grades 5 through 10 aligned to next generation science standards. We have widgets to support inquiry that capture student performance. These were designed using evidence-centered design. Then we have performance assessments, reports, and alerts on students' practices and skills. And this required breaking down the practices into subcomponents. And then you have data mined rules and engineered rules for assessing, scaffolding, and alerting. So there's a whole, this is a kind of a technological component here. So the Ngss architecture, there's quite a few, as you can see. This system's been in development since 2008. So you have a very rigorous logging infrastructure, simulated student testing infrastructure, scaffolding infrastructure. I mean, and this is really due to the brilliance and talent of the technical team and not to myself. I just envision things and they turn them into code. It's a great job, I have to say. And the Ink Blotter architecture has these various components, and these things are tied together. So when the teacher walks over to the student, she gets an alert on Ink Blotter, walks over, hits the record button, It triangulates all that data together as a nice little bundle and records it with the voice. So we have exactly what the student did, what the teacher said, and then the next performance all bundled together. So our virtual simulations provide an opportunity for authentic inquiry. They share a lot of perceptual affordances to the actual thing, right? That's not a trivial point, but I'm not going to belabor that point. And with simulations, students do these NGSS practices. We use evidence-centered design to design the student model, for example, which I think is the most interesting. It includes the subcomponents for each NGSS practice. This was based on piloting kids one-on-one, where we started with a physical ramp apparatus, literally watching a kid, roll a ball down a ramp, and looked at the kinds of things they did, where they went wrong, how they engaged in inquiry with a physical apparatus, and then we have piloted and repiloted every aspect of the system. So we operationalize in concrete for scalability and auto scoring these practices, and we have a new chapter coming out with Bob Mislevy on that process. So then we have machine learning, patented algorithms under the hood used for assessment, scaffolding, and alerting. These were developed using text replay tagging that are used to develop canonical models of what it means to demonstrate skill and in turn develop these algorithms. They handle the variability of student data. And we've now done this for all inquiry practice with very close match to human scores. And these were validated over multiple topics, over diverse student body, etc. And generalizability is tested with kids not used to build the model, a held out test set. So here's a little summary. You collect the data, you build your text replay clips, you tag the clips for skills, you define the features with rapid minor, and then you validate them. So now I want to drill down on a couple of studies that are really near and dear to my heart because I think they exemplify the power of this system. So one is testing the robustness of scaffolding. Our funders wanted us to test the robustness of REX and really measure how well students are able to transfer their practice knowledge to the next practice. So why would we scaffold? Well, first of all, students have inquiry difficulties and might engage in unproductive or haphazard inquiry. Some of my very early work in 2006 in this kind of domain substantiated that. Students lack metacognitive skills to know they need help. So students are not good at knowing when they need help. That's why you have to proactively jump in. So we don't have on-demand help because kids also abuse the help. They'll click down to get the bottom out hint so that they know exactly what they have to do. But we want them to learn. So we jump in real time when we detect that they need the help. And just-in-time help can support learning, and it's the best time to develop deep learning in kids, or adults for that matter. So why use an agent? Well, we use an agent because it may increase engagement and motivation and makes learning more interactive. So Rex here was based on the visual of Rex, the bow tie, the lab coat, the spectacles, etc. We based this on interviews and surveys with 400 kids, and we graded the color and all these things. So this is the guy that we came up with. So Rex supports students on common difficulties with the practices. I'm going to give you a few here. We really combed the literature, reviewed a lot of literature. In fact, Clark's early work from his dissertation came up here. So students regarding questioning or hypothesis formation, they have difficulties forming hypotheses and they don't understand what an independent variable is. They understand what a dependent variable is, but they don't really understand an independent variable. In terms of carrying out investigations or collecting data, they don't test their articulated hypotheses. So they make one and then they get in and they do something different. They may not gather sufficient or appropriate evidence to test their hypotheses, like they run only one trial or run the same trial over and over, or they change too many variables in the same trial. And Deanna Kuhn at Columbia has shown that even adults do that if they're not scientifically trained. So why would we spontaneously expect students to learn this skill if adults don't even know how to do this without training? With regard to analyzing and interpreting data, they don't link their data to their hypotheses or their claims. They draw conclusions based on confounded data, and they engage in confirmation bias. It's really important, even adults do that. And regarding argumentation, kind of broadly construed explanations, argumentation, etc. They use inappropriate and insufficient data in providing reasoning for their claims, and they have trouble linking their data to their hypotheses, which of course is the point, right? That's why they do experiments. So what we do is we scaffold these. These are triggered by EDM-based algorithms in real time. They're delivered via REX, and they provide students with multiple levels of support. So we do what's called orienting support, conceptual support, procedural support, and instrumental support in that order. And some students, this is interesting, some students who would prefer just to get the bottom out hint told the teacher, I really hate REX. And then she realized those are the kids who just are trying to click to get the bottom out hint. And she said, well, you know, if you just like REX, read what REX is saying and follow his advice. And they started doing that, and they started learning. So they're happier now. All right, so with regard to this transfer study, what we did was we had 107 kids, Northeast. They did the animal cell activity, which has 3 different tasks with scaffolding. So they started with animal cell, of course, 3 driving questions. Then 40 days later, they did plant cell with 3 driving questions. Then another 40 days later, they did genetics, which is substantially harder with 3 driving questions. Then 90 days later, they did natural selection, okay, with 4 tasks. They formed questions, they carried out investigations, they analyzed, interpreted data, and communicated findings using claim evidence reasoning format. And REX was used for only animal cell, and then we dropped them out because we're testing the robustness of the scaffolding, and this was for an NSF grant. So here's an example. They have a goal. The Golgi body is not receiving enough protein. Investigate how you can fix this problem. And so you have, you know, what I will change, and so you have some variables here, and then what will happen. And this is one example of an interface. We have a variety of interfaces. Then what they do, they go to collecting data, the Golgi body. Their goal is depicted at the top, and then they have their hypothesis. And then they manipulate the number of organelles, which gets at the DCI about the organelle's function. And then what they do is they say what I changed, and they use this kind of widgetized, scaffolded, widgetized process to create a claim. What happened, and then my analysis. Does it support or refute my hypothesis? Then what they do is they select their data. So they see their data table, and they go and they select the data. So we are able to determine if they pick sufficient and appropriate data for their trials. And then they write claim evidence reasoning, but I'm not going to drill down on that today because we weren't scaffolding this at that point, this study. So students' inquiry performance is captured and assessed at the practice level and the sub-practice level using knowledge engineering and educational data mined algorithms for forming questions, carrying out investigations, analyzing data, and warranting claims via the widgets. And then these were validated in prior studies. Then we used repeated measures, ANOVAs, to investigate whether students' performance on each of the 4 inquiry practices was robust over time. So you have animal cell in which the scaffolding happened, then we drop the scaffolding off, then plant cell 40 days later, genetics 40 days later, which is substantially harder, and then natural selection 90 days later. So you have a significant time by practice interaction as well as a significant multivariate interaction. So, and the within subject effects are also significant. So what's interesting is you see at time 1, where they are on the various practices. Time 2, 40 days later, we've dropped REX off, and you see a significant increase. So not only did they perform on par, but they actually got better. Then we introduced the 3rd activity, which is genetics, which is inherently more difficult than either of the cell activities, and you see a slight degradation in the performance on each skill, which you would expect. And then we did 90 days later, the 4th activity, and you see that the performance is up again, and these are significant effects. So with regard to study 1, the algorithms and architecture enable real-time scaffolding by REX. So well-defined, targeted adaptive scaffolding in one topic in INKITS can actually be robust enough to support students' inquiry in the next, even after scaffolding is removed. This is robust across topic and time, 170 days later from initial. So that's very interesting. And so REX can greatly support the acquisition and honing of these variables. And we have a series of publications that I can send you on that if you're interested. So now I want to talk about identifying the messy middle. The messy middle is an assessment term where you have a broad range of kids, and it's something. They compared, no, they're serving as their own control.
But they all got scaffolding.
At time one, yeah. But we do have studies like that with no scaffolding versus scaffolding. And what we've done in those cases, Raha Musavi and Mike Salpedro did this for their respective dissertations, where we tested the kids on certain skills and picked only kids who didn't know those skills and then randomly assigned them. So it was even more rigorous than a gold standard. So getting back to this messy middle idea, you know, with respect to assessment, it's often easier, or it is easier to assess kids who are really highly skilled, right? It's also easy to assess kids who are really not that skilled. But the kids in the middle, the messy middle, they're hard to assess. Well, you have this messy middle for inquiry because we expect kids to do so many different rich practices. And we also expect them to be able to do argumentation. And so we suspected there was a real messy middle. It was like the messier middle. And I also suspected there were kids who could do inquiry but not describe inquiry in words due to lack of sort of literacy skills, or even just a lack of how do you turn that STEM knowledge and the STEM practices into an explanation. So I suspected there were some of those kids. We all know there's kids who are just parroting, right? We all know that. Anybody who's been in the classroom for 30 seconds knows there's kids who are just parroting and they actually don't really know once you scratch the surface. What was surprising to me was how many we saw at the tails, the Billies and the Johnnies. So we wanted to empirically demonstrate this. So we did this. So we'll put these into two categories loosely. You have the doing, generating a question, forming a hypothesis, collecting, analyzing, interpreting data, selecting data to warrant a claim. We'll put that in the doing category. Then we'll put the claim evidence reasoning in the writing category, okay? Because this requires a lot of argumentation explanation skills from students. So what we had was 293 middle school students in 6 public middle schools. And we used our density lab, and this was the shape of the container activity. So what they do is they determine how the shape of the container affects the density, and then they run with their hypothesis, they collect data, they analyze their data, they select the data that supports or refutes their claims, and then they write the claim evidence reasoning. So their actions on the doing are assessed via educational data mined or knowledge engineered rules. Then the claim evidence reasoning explanations are scored. We developed rubrics with Haiying Li, who's our former postdoc, and Rachel and myself. And so what we had was we developed rubrics. We did a ton of hand scoring, and some students from Rutgers were also involved in undergrads. And we had 2 raters hand score student explanations for the Ngss stage according to the claim evidence reasoning subcomponents aligned to the science education argumentation literature. For example, for evidence, we're scoring, is it sufficient, is it appropriate? Because that's what, say, Sandoval and et cetera do. So the inter-rater reliabilities were quite high, 0.96 for claim, 0.97 for evidence, and 0.077 for reasoning. Now we're auto-scoring because we've developed NLP algorithms to auto-score students' writing, and we have quite high correlations between humans and algorithms, which is, of course, what you're looking for, 0.90, 0.94, and 0.86 for CER, respectively. So then we use K-means clustering to say, well, how many kids are in the messy middle, right? So how many kids are like Billy, who's really good at doing inquiry, but not very good at describing and claim evidence reasoning? Or how many kids do we have that are like Johnny, who actually don't know very much about inquiry or science, but are actually really good at parroting, this shallow parroting, but the teacher's gonna grade them as correct, right? So we were really surprised to find that 49% of kids were in the messy middle. 49%. That's a huge number. We've replicated this a number of times. It's never lower than 30%, and it goes as high as 60%. So if teachers are relying on students' claim evidence reasoning as a way to assess students on the practices, they're likely they're often incorrect in their assessment of students' skills. Even when they're doing the claim evidence reasoning, there's so many facets to that they might actually be misassessing students' skill level on that very precise practice. So I want to give you some examples. These are real examples from our system. So this is a kid, we call him Billy. He's a false negative. He sufficiently warranted his claims in the experiment, so he could do it. He picked the right, but he says, my data shows that the density doesn't change. Right? That's not enough given the NGSS performance expectation. Here's another one. He ran a successful investigation that analyzed the data, but he didn't know what to write. In fact, he wrote, I don't know. So if the teacher's relying on what he writes, this kid Billy, or is our science genius, our future, our STEM economy is relying on kids like this, he's saying, I don't know. The answer to this is in my claim, I think. So this is very, very coarse, very terse kind of explanations this student is doing. Here's Johnny's. Johnny's are false positives, the kids who don't really know what they're doing, but they're really good at talking the talk, right? Okay. So here's a kid who wrote about an experiment he did not conduct. Okay. So in the lab, like he might be just pretending to do something or doing a different experiment, but he knows that this is the question that he has to answer. So he says the shape of the container, liquid, it does not affect the overall density of the liquid, which is in fact correct. But he actually didn't even run this experiment, right? And then he says if you change the shape of the container from wide to narrow, he didn't change the container from wide to narrow. He only has wide. So he's picking up the buzz in the classroom. He's articulating it. He's actually, if the teacher is scoring what he wrote here, if he wrote this in open response format, he's actually being deemed as competent, but in fact he's not. He does not even have the data. Here's another example. He miscalculated the data, but he reported the correct data. So he's getting the answer from somebody else, right? And by the way, I don't want teachers to use this as aha, you're cheating, I got you. I really hope teachers are not doing that. What I hope teachers are doing is going up to somebody like this student and saying, hey, you've written some scientifically accurate things. Now let's go back and do the experiment and marry these things together. That's what I hope teachers are doing with this kind of information. Or walking up to a student like Billy and saying, you're doing really well at all these practices. Look at how you're doing on ink blotter. Now let me help you on the claim evidence reasoning statement. What are those aspects? Or let's let Rex help you on how do you generate a claim? How do you generate evidence? How do you select that evidence? How do you then substantiate that in your reasoning statement? That's what I want teachers to do. So if you have that data in their hands in the form of an iPad in real time, they can actually do that. They can, in fact, stop the class. If everybody's selecting inappropriate data, you can stop the class and have a conversation about how do you select data that's appropriate to match your claim and put data up on the board. All right, so you have these quadrants. What's interesting about it is in the high doing, high writing category, they don't really need Rex, right? But in all three other quadrants, you really need Rex working in real time, in tandem, to help kids in real time when the opportunity for learning is greatest. So with regard to study 2, our findings demonstrate that there is this messy middle in students' inquiry performance, and this can result in false negatives and false positives if there's a over-reliance on written assessments. Now, don't get me wrong, writing is important. Reading and writing should not go away, and we need to hone that. But this is what you need to use this data to differentiate students' skills at the other practices from their skills at articulating what they know about science and build those up. We've replicated this a number of times, and consistently it's 30 to 60% of kids are misassessed if you rely on what they write. So assessments need to assess the full complement of inquiry practices in science policy documents because writing alone will not be sufficient for a large proportion of the kids. Now, in terms of an overarching summary, Ngss is based on a theory of human visual information processing, model-based learning, students' difficulties with inquiry, students' misconceptions in science, and evidence-centered design in order to address and support measurement of inquiry, identification of mixed competencies across the practices, students' learning of NGSS and transfer, and in turn scientific literacy, and also teachers' pedagogical practices to improve students' inquiry and in turn their science literacy. In terms of formative assessment, this eliminates teachers' grading of the practices, it provides formative data on how students conduct their inquiry, provides student level and classroom reports, and provides alerts at the subcomponent level that are actionable alerts. And as I said, what we're now designing are something that the team calls TIPS, right? What do they call technology?
Teacher inquiry practice support.
Yeah, just came up with this for ICLS, right? Like 2 weeks ago. So TIPS, so the teacher will get an alert if he or she doesn't know what to do, because some teachers really do not know what to do and they default to the content support. They can drill down and decide, and be given that information about what to do. And what we want to do is track how the access to that lower level tip, that more specific level kind of over time, decreases over time as they become more and more comfortable with the practices. So this permits classroom integration for practices or for materials like these to get at the practices. So it's really self-assessment and blending learning opportunities together. Now, in terms of measurement, this approach combined with data mining can influence the design of future assessments that are scalable. So keep in mind that our goal was scalability, right? So there are people who may have who may have a more nuanced interpretation of the various practices, but we really wanted to be able to scale this. And so we worked very closely with teachers and students to figure out what are the subcomponents to each practice and how could we use instrument activity design and instrument activities in order to distill that log data and then react in real time, alert, etc. So I'd like to acknowledge my team. We have Mike Brigham, software engineer. We have Rachel and Amy here. Haiying, who's a postdoc, who's now at ACT. Victor Brusca, who was here. And then on the apprentice side, because these activities now in platform are being productized through a company, and Mike Salpedro takes the lead on that, and Cam Betts, who are former PhD and master students, Jason Kleben, Charity Stoudenrouse, and Pat Rowan, who's a graphic designer. So that's sort of the broader team, and we have some new members like Mariel and hopefully Kyra. So now I'll open it up to questions. Thanks so much. I love to talk about this project. It's my baby, Everyone loves their baby. I love my baby too. So I'll open it up to questions.
I had a question.
Sure.
You talked about Brex and motivation, and I was wondering if there's any affective issues that can be measured or.
Well, we did measure affective. I mean, that's an interesting word. Well, I'll tell you what we were measuring: carelessness, frustration, boredom, confusion, disengaged from task goal. But the thing is, as a psychologist, I kind of worry about the ontological description of those variables and how, like a computer scientist kind of came up with a lot of these, and this is a log signature for confusion, and this is a log signature for boredom. And some of those I think have been validated really well. Others I still kind of am somewhat questioning as someone who comes from the field of psychology. But the way that we come at it is if we can know when a student is off task, which we do, we don't worry so much about whether they're bored, frustrated, confused, etc., or they're having a bad day. We just help them with what they need. We kind of get the job done.
Right.
But with my another postdoc who worked with me, Arnon Hershkovitz, we did a fair amount of affect work. And I think it's interesting and I think it's valuable, but we bit off a significantly big chunk that I'm going to kind of stick with the assessment aspect. At the back? Oh, sorry. Go ahead.
How many lessons are per grade level?
That's a good question. I mean, we have about 150 activities now.
So I guess my question is, how is it supposed to be implemented in the classroom? So the teacher would teach like a unit, and then would this be the end of the unit, or like?
Well, it could. It could
or
be.
the new teacher like solely rely.
You could get baseline. No, there's not enough content in here, right? These are like aligned to the core DCIs and NGSS. So they do what they would normally do, and then they're designed to kind of drop in, get the information they need, and then continue with the unit and hone instruction accordingly. But teachers use them as pre-assessments, post-assessments, summatives, review, for kids who are really advanced, for kids who need remediation. So there's lots of ways. I mean, you know, teachers are actually really creative with the resources that you give them. And although we design these with formative goal in mind, and that's how mostly teachers use them, they're also really like, oh, I'm going to drop in and figure out how, you know, where they were now in September compared to June, for example. So, Drew?
Yeah, so you've got this, you know, very impressive system, and you've got lots of models running underneath it. So let me just pick two. One is Rex and the pedagogical approach, right? So it's a model of how to give feedback. And then there's also the model of you're giving feedback, you're giving information to teachers, right? How do you go about, you kind of gave us the end state, but what's the process by which you actually develop these approaches and theories that drive the decision, you know, how this all plays out? Is it theory? Is it empirical work? Is it intuition?
Yeah, so that's a good question. So in terms of the scaffolding, we looked at, you know, the earlier work out of intelligent tutoring systems. So we use the orienting, procedural, conceptual, instrumental framework because that's been very successful. And that seemed to, you know, that we get actually fairly good results, as you saw in the scaffolding. So kind of slicing the pie that way and giving kids that level of support seems to make sense. So when we're running an empirical study, then we don't actually, we want the teachers to not help the kids independent of that. Now, with respect to...
And when do you decide when to interfere?
Oh, we interfere when, I think there's a trigger. It's not the split second they do. We let them flounder a little bit. But we don't have like a student model under the hood that's saying, okay, Drew always does 6 trials where I don't know what he's doing, and then we're gonna jump in on 7 because we know Drew. It's not like that. Right. It is a set of algorithms that are determining how much fooling around there looks like is going on. If there's disengagement, if they're closer, further, closer, further, closer, further, you know, so there's a whole series of kind of metrics that we're looking at based on machine learning that have predictive validity, right? Yeah. Oh, sorry. Go ahead, Clark.
I'd like to know more about how you determine that students don't get independent variables.
So that's actually quite an easy thing in our work because we have a widgetized process by which they produce a hypothesis, and they'll sometimes specify 2 dependent variables. And Rex will jump in and say, you've specified 2 responding or dependent variables. Please.
They specify, what does it look like to specify?
Like it's we have the widgets that I showed you with like pick which variables, or we have like pull downs. So we have a variety of different widget structures depending on the activity. And so that's, you know, that is, and we also know from your work, that's a problem with students. They don't understand independent variables very well. In fact, many people don't understand independent variables very well. And that's not a trivial thing because you need to know an independent variable in order to make a hypothesis. You need to know what an independent variable is in order to run your trials. You need to know what an independent variable is to pivot around it in terms of data interpretation. So that's a really key thing, right? In terms of the inquiry processes and practices. Kyra?
Forgive me for not knowing, you know, the full program of Ngss, but my question is, the activities that you you've structured, are they for also outside of the classroom too? And are you using Rex as a tutorial or a tutor for kids who are using this outside of the classroom? Are they using Rex as a tutorial also?
Yeah, that's a good question. Yes, absolutely. So the system saves states, so wherever the student logs off, that's where it'll take them back. So the teacher will say, if you didn't finish, log on tonight, or go to the library and log on and finish, or sometimes reassign. You know, you look like you need a little more practice, let me reassign these. And the teacher will give another code, and then the student can do it, and then we measure how well they've done on the second iteration.
Okay, so is there an assumption that the student is technology savvy, meaning they know how to navigate your program outside of the classroom without any structure?
Well, they know how to navigate because they've used it in their classroom, right? We don't have, you know, such eager kids who are downloading it and just, you know, I want those kids. I wish I had some of those kids. No, nobody's doing that. Right? Teachers are and running as students, but yeah.
Okay.
Yeah. Yes?
So with that, like, the program isn't adaptive in the sense of, let's say it's a sixth grader and they are struggling on a certain material, it won't drop down to like the fourth grade level of that material?
No.
Okay.
No, it's not adaptive in that sense.
Okay.
So it's figuring out what difficulty they're having with the respective practice and then giving them support, right? So it's adaptive in that regard. Yeah. Are there any other questions, Mariam?
No, it's just a more of an overarching question. I was just curious, what was there's understanding what caused the U.S. to go from 13, I think you said, to 24? Is it that others have gotten better, or is there something?
Yeah, I don't know. Maybe some other people know why we've dropped from 13th in 2009 to 25th.
That's a significant.
It's a significant
People
drop.
don't test it, honestly. Like, in a lot of countries, they only test like the highest level of students too. So it's some misinformation.
Just some, yeah.
It's true and misinformation.
Right.
Yes. One National Science Board report in 2018, and they were like, oh, it's that other countries are just adopting more research-based methodologies or something, but they don't actually, I don't know how exactly they're measuring.
Right. Yeah, right. Drew? Oh, sorry, Clark.
This is asked in the context, nobody expects the curriculum to cover all the science practices of the genome. I'm just trying to understand what either is or could be evaluated in the system. So here's an example of a case I think is interesting. So I'm wondering if either you can assess it now, or is it something you can imagine could be assessed in Ngss, or you just, and then it might be just something that's not what Ngss is designed for, which is fine too. So here's the thing I'm wondering about. So in lots of cases, you have two different models. And I think a really important intellectual achievement for students is to come to understand that the same evidence, good evidence, not confounded evidence, but good evidence, so can be taken to support both models depending on how you interpret the evidence.
Mm-hmm.
Is that something that can be assessed by Ngss at present? Could it be in the future, or is it sort of just outside the scope?
Well, it's not at present. It probably could. So we're, doing a lot of work on mathematizing now, and Rachel's doing some of this work. And as part of that, we're thinking about the model, the qualitative modeling. So I can imagine perhaps a phase where there's this qualitative modeling aspect, right, that's aligned to something like that. So we haven't done anything like that. We're kind of reading the literature, including yours, on model-based reasoning, the models that need to sit between, students' skills and students mathematizing, but it's mathematizing in the context of science inquiry, but that's a really rich modeling enterprise. But we haven't thought about model evaluation in that sense. We have thought about model evaluation compared to real world data. How does this match the real world data? Where did your model fall short? So you could easily imagine how you could have then two models and then how you would evaluate the evidence for each model in a similar framework as a model evaluation task, which I think is really rich, right? And as we get into the mathematizing, we're going to need to probably build this modeling component because there's so many kids who are poor at it. What's interesting about, my technical team, they all have computer science degrees, and so of course they're very fluid in math. And so they make these assumptions about what kids are able to do, right, in math. And I'm like, when's the last time you were in a math classroom? I mean, really, right? Because kids need those qualitative models as a step to get to the really deep understanding of the mathematizing. So, and I think, you know, if you look at at the NGSS expectations for performance, I mean, that's what they're talking about. So people aren't going to just be able to go from something like this to the mathematizing. There's going to be a lot of students who are going to be lost. Now, if we can give the teachers rich data, they can maybe fill that gap for now, and then we can study that iteratively and build something for, you know, more qualitative modeling. I think that's probably what we would do, what we will do. So, is there anything else?
Well, people can come up, but thank you so much. It
Oh,
was
thanks,
great.
thank you. Yeah, we're pretty excited. We're in 50 states now, either in trials or research or whatever. So we're getting some traction, and getting some traction in Asia. So that's exciting.
What about rural and urban areas?
There's a really deep, you know, a rich and broad mix of schools that use this. Very high-end schools where, for example, you know, the parents expect a really detailed, written, qualitative report card, and you have teachers drilling down in our system and getting exact student performances and saying, well, this was Billy in September. Now look at Billy now in March. And the parents love that, right? And then also schools where they have the tech, like we worked in a school where they spoke 90 languages in Fitchburg, Massachusetts, or used the computers were from the prison. They were hand-me-downs from the prison, and we have run this. So yeah, wide range of demographics.
All right, well, have a great end
Yeah.
of the semester, everybody,
Yes.
and we will catch you on the other side.
Thanks.